let me pull up a LT Spice file that I made. I think I remember making. We'll find out in a second. Noisy comparator. There we go. All right. So what I have shown here is effectively what we did in class at the end of Monday's class meeting. I've got my supply voltages. For whatever reason, this time I have them as plus and minus 10 volts, but effectively I just designed a simple comparator. And if we look at the output voltage of this comparator as compared to the input voltage with some noise on top of it, we see that problem that we saw at the end of the last class meeting, where when the noise, when there's noise around the reference voltage, our output swings wildly. And so over here on the right-hand side, I have designed a circuit that fixes that to some extent. So I just want you to look here and see the same input voltage, Vn plus noise, is being applied at this terminal. Our reference voltage is exactly the same. The only changes that we've made is the installation of this positive feedback resistor network down here. And we're going to talk in a minute about how this works. If we look at our output voltage of this function, we can see a couple of things. First, for the most part, there is no ringing or oscillation or anything like that. We have this little bitty hiccup right here due to the noise in this region, because it just wasn't sure what to do at that point. But once it kind of gets locked into its thing, once we exceed what's called the upper trigger limit, the output of our circuit is going to stay high. And once we get lower than what's called our lower trigger limit, our output is going to stay low. And the values of these upper and lower trigger limits are dependent on this resistor network. So let's look at this from a slightly different perspective to see if we can get a better idea of where our trigger limits are. So I'm going to plot this as a function of Vn. So it looks to me like one of our trigger limits is somewhere close to 1 volt. So it's transitioning from either low to high or high to low at around 1 volt. And we've got another one over here that's somewhere a little bit less than 7 volts. Okay. So that's based on those resistor values. So now let's do a little bit of math and circuit analysis to figure out why they're there. Okay. So for today's class, we're going to be talking about positive feedback circuits. And the first one that we're going to look at is called this first, I guess, class of circuits that we're going to look at is what are called Schmitt triggers. And we're going to look at both a non-inverting Schmitt trigger and an inverting Schmitt trigger. Okay. So let's start by drawing our circuit. So here is our positive supply voltage, VCC plus, our negative supply voltage, VCC minus, And we have our input and output terminals. So connected between the non-inverting input terminal and the output terminal, we are going to have some resistor that I'm just going to call R2. And then between the non-inverting input terminal and our input signal, we're going to have a resistor that I'm going to call R1. And so this is the resistor network that was added to our open loop comparator circuit. And then I'm going to apply my reference voltage here. So because this is a positive feedback circuit, I mentioned this in class on Monday, we have an expectation of a decreased linear range. And this means that the output voltage will practically always be BCC plus or BCC minus. It only has two stable operating points, either saturated high or saturated low. Okay. Linear amplification pretty much is not a thing at all with a positive feedback op-amp circuit. All right, so let's draw a practical op-amp model representation of this thing so we can do a little bit of analysis here. Okay, so as per usual, I'm going to start with just my op-amp by itself. Let me turn off my email client, or that's going to pop up constantly. So here's our input resistance Rn. Here is our non-inverting input terminal. Here is our inverting input terminal. This potential difference is our differential voltage Vd. There's our dependent source. Our output resistance R out. And because our output terminal is open circuited, this will be our output voltage. So first thing I'm going to do is I'm going to connect my voltage sources, right? So I can see that I have a reference voltage connected between my inverting input terminal and ground. So that means Vref is going to be right here. I have a resistor R1 in series with my input voltage source between the non-inverting input terminal and ground. So let's do something like this. And I have a resistor that is connecting my non-inverting input node to my output node. So we're going to put our feedback resistor up here. This is R2. We are going to make an assumption here that is rather important. We talked about this a little bit in Monday's class meeting. So we are going to assume that the resistance Rn of the op-amp itself is much, much greater than the resistances R1 and R2, meaning that we're expecting R1 and R2 to be roughly kilo ohm size resistances and Rn to be roughly mega ohm size resistance, which is how we would normally bias an op amp for an input resistance that's on the order of mega ohms. So what are the consequences of this assumption here? Okay, so let's think about things really quickly. So there's going to be some current that's flowing through this resistor R1, right? Where we're assuming that, Vn is a non-zero voltage. The current is flowing into the non-inverting input node of the op amp, okay? Now, connected to that node, we have a resistor R2 that is significantly smaller than that resistance Rn. So there's going to be some current here. I'm going to call it I plus, but it's going to be extremely close to 0 amps. It's not going to be 0 amps. It's probably going to be on the order of microamperes or nanoamperes, but it's going to be very, very small, okay? And then the overwhelming majority of that current that I have listed in red is going to then wind up flowing through that resistor R2. Are we all okay with this assumption based on the size of the resistors and all that kind of stuff? Okay. Now, what's the consequence of there being effectively no current flowing through our input resistance? The voltage drop across that input resistance is going to be incredibly low. So effectively, this voltage here seen at our non-inverting input terminal is going to be approximately whatever our reference voltage is. Because if there's no voltage drop or very, very small voltage drop across that resistance Rn, then that's just going to almost short circuit Vref up to that node. So under those constraints, let's do a little bit of circuit analysis. So if I apply Kirchhoff's current law at the non-inverting input node, what I'm going to have, and let me change the direction of this arrow. Oh, I could have left it that way. I guess we'll just do these two currents and set them equal to each other. So the current flowing through the resistor R1 is going to look like Vn minus approximately Vref divided by the resistance R1. And this will be equal to the current that's flowing out through the resistor R2. And so this is going to look like Vref minus V out over R2. All right, so what we can do is we can move the Vref terms to one side of the equal sign and the non-Vref terms to the other side of the equal sign, and we'll see something like this, right? So I might have Vn over R1 plus V out over R2 is equal to Vref over R1 plus Vref over R2. Okay. I'm now going to multiply Actually, let's expand this out very slightly here. So that's going to look like VREF times 1 over R1 plus 1 over R2. Now, what is 1 over R1 plus 1 over R2? I know this is kind of an odd question, but what does that look like? What does it remind you of? Parallel resistors, right? So if I had 1 over that thing, that would be the resistances R1 and R2 in parallel. So this is just effectively VREF divided by R1 in parallel with R2. So what I'm going to do is I'm going to multiply both sides through by R1 in parallel with R2. So in doing so, that's going to give me VREF by itself on one side of the equal sign. And then I'm going to have Vn over R1 multiplied by R1 times R2 over R1 plus R2. And then I'm going to have V out divided by R2 multiplied by R1 times R2 over R1 plus R2. And I can see that this R1 cancels this R1, and this R2 cancels this R2, leaving me with VREF is equal to Vn times R2 over R1 plus R2 plus V out times R1 over R1 plus R2. And it's this equation right here that actually tells us where our upper and lower trigger limits are going to be. So this is kind of like the characteristic equation for this non-inverting Schmidt trigger circuit. So let's define a couple of those here. So the upper trigger limit voltage, which we're going to call V UTL, is the input voltage that causes, bless you, V out to change from VCC minus, a low state, to VCC plus, a high state. Okay. So if we wanted to solve for our upper trigger limit voltage, we would have something like this. VREF would be equal to V upper trigger limit times R2 over R1 plus R2 plus V out. Well, V out in this case will be VCC minus because that's the low state, right? So it starts at VCC minus, and once we exceed the upper trigger limit, it swings high. So if we look at our circuit that I have here in LT Spice, my reference voltage is 3 volts. My resistor R1 is 3 kiloohms and my resistor R2 is 10 kiloohms. So let's write those things down here, right? So Vref, 3 volts, R1, 3 kiloohms, R2 is 10 kiloohms. So if we were to plug in these numbers, we could solve for our upper trigger limit voltage, right? So we would have 3 volts is equal to our upper trigger limit voltage times 10 kiloohms over 13 kiloohms plus VCC minus, which I didn't write down, so we'll do that real quickly. So if I'm not mistaken, VCC plus was 10 volts and VCC minus was negative 10 volts. Let's just double check that really quickly. Absolutely. And that's going to look like 3K over 13K. And we can throw that into our one equation, one unknown numerical solver, or do a little bit of algebra either way. And what we should find is that our upper trigger limit voltage should come out to be 6.9 volts. If you want to throw that into your calculator and verify it, you're welcome to do so. But if we look at our graph here, that seems like a pretty darn reasonable estimation. So let me grab a mouse. If I remember to bring one, which I hope I did. So what I'll let gibber is about. Let's see if we can find that voltage on our LT Spice circuit, which it looks like I accidentally closed. Run the simulation, be out. Let's change that to something more visible. So if I mouse over this thing here, I can give myself a cursor. And so I'm just dragging this over here. Horizontal says 6.7 volts. Okay, so not quite 6.9, but pretty close. And it's not going to be exact because of the assumptions that we've made, right? But we have a pretty darn good estimate here. Now let's look at the lower trigger limit. Everything changing to this classroom. Our lower trigger limit voltage is defined, actually, let me sneak this in. VLTL. It's defined as the input voltage that causes the output to change from VCC plus, a high state, to VCC minus. So our equation is going to be almost identical. V reference will be now V lower trigger limit times R2 over R1 plus R2. And this time it'll be plus VCC plus times R1 over R1 plus R2. And substituting in our numerical values, this is going to look like 3 volts times VLTL times 10 over 13 plus 10 volts times 3 over 13. And if we solve for that lower trigger limit voltage, it comes out to be 0.9 volts. Once again, agreeing pretty well with what we saw on the graph. And we can check that out specifically by just moving our cursor over here. So about 0.97 volts. So our lower trigger limit is a little bit higher than we would expect. Our upper trigger limit is a little bit lower than we would expect just because of the assumptions that we've made, but nothing too wild here. One thing that is important to point out when you're designing a circuit for specific upper and lower trigger limits is that your reference voltage needs to be between them. If it's not, you'll never be able to exceed the upper trigger limit or transversely go below the lower trigger limit. I know that should be kind of common sense, but the reference voltage must be somewhere in between the upper and lower trigger limits in order for this kind of circuit to work. I'm mentioning that very specifically because if you look at your design projects, one of the first design project prompts I give you is designing a Schmidt trigger circuit to make a better analog to digital converter than the one that we designed in our last class meeting. So if we look at that design prompt really quickly, pull it up here. It is literally the first one. In digital logic applications, a 5-volt signal represents a logical 1 or high state. A 0-volt signal represents a logic 0 or low state. Yada, yada, yada. I'm asking you to design a 1-bit analog to digital converter that takes an analog input voltage signal ranging from 0 volts to 5 volts and outputs either 0 volts or 5 volts with an upper trigger limit of 3 volts and a lower trigger limit of 2 volts. So what would be a good choice for a reference voltage? Yeah, just something exactly in the middle to make the math really, really easy. I'm mentioning this explicitly to you guys because for whatever reason, students in previous quarters just did not seem to fundamentally understand that it needs to be between the trigger limits in order for it to work correctly. So I'm spelling it out to you here very explicitly, okay? So now that you know what your reference voltage is, what would your supply voltages be? 0 and 5 volts. So all you have to do is figure out what resistor values get you an upper trigger limit of 3 volts and a lower trigger limit of 2 volts, and this design problem is done. Realistically, this should take you less than 10 minutes. All of these should take you 10 to 25, 30 minutes tops, by the way. So this shouldn't be a big, huge, daunting thing. Okay, so let's take a moment to learn how to read this graph because this is a pretty interesting thing and it'll help explain what's going on in the Schmidt trigger circuit. So effectively what we're doing is we're sweeping our input signal from negative 10 volts all the way up to positive 10 volts and then back down from positive 10 volts to negative 10 volts. So effectively what's happening here is that our output voltage signal is low at -10 volts until our input voltage hits our upper trigger limit, at which point our output voltage transitions from its low state to its high state. And then it stays high. And then when we come back down, our output voltage stays high until our input voltage gets lower than our lower trigger limit. It drops low and then it stays low. And that cycle just repeats over and over and over again if we were to allow our input signal to cycle. Okay. So effectively, this type of circuit demonstrates what's called latching. It's holding on to an output value until some control stimulus tells it to change, okay? This can be used in an awful lot of situations in control circuits and all of that kind of good stuff. So you'll definitely see circuits like this again. All right, so this circuit was a non-inverting Schmitt trigger. So in order to make an inverting Schmitt trigger, we are literally just going to do the exact same thing that we did for our comparator. We are going to switch the position of our input voltage and our reference voltage. Okay. So that means we're going to have a circuit that looks something like this. So starting with just our op amp, where this is the non-inverting input terminal and this is the inverting input terminal. Here's our output terminal. We're once again going to have a feedback resistor, R2, placed between the non-inverting input and the output. We're going to have a resistor connected between the non-inverting input and one of our voltage sources. So this is going to be R1, but this time we're going to apply our reference voltage here, and we're going to apply our input voltage here. So literally, all we have done is just swapped those two voltage sources in our circuit. So instead of doing a bunch of circuit analysis, what do you think we're going to do to our equation? Swap Vn and Vref. Why do we need to do literally anything else, right? So this particular circuit is governed by the relationship that Vn will be equal to Vref times R2 over R1 plus R2 plus Vout over R1 over R1 plus R2. Our definition for our upper and lower trigger limits remain exactly the same. The upper trigger limit is the voltage that's causing, or excuse me, the input voltage that's causing the output to transition from a low state to a high state. The lower trigger limit is the input voltage that's causing the output to change from a high state to a low state. This equation means we don't even have to use a numerical solver or do any algebra to rearrange anything, right? If we want, just for the sake of argument here, our upper trigger limit voltage is just Vref R2 over R1 plus R2 plus VCC minus R1 over R1 plus R2. Literally put that in and we get our upper trigger limit voltage directly. Same thing for our lower trigger limit, VLTL, Vref R2 over R1 plus R2 plus VCC plus R1 over R1 plus R2. Definitions stay the same, but because we're using an inverting configuration, we're going to wind up with different trigger limits in this case. All right, so that's Schmidt triggers. That's one application of positive feedback. Now, let's look at another commonly used application of positive feedback. So this circuit is what's called an op-amp astable multi-vibrator circuit. And we'll see in a little bit that effectively this is a circuit that we could use to get clock. We're going to have regularly repeating oscillations here. So this circuit is pretty interesting, at least to me, and you'll see why in a moment. Let's draw things out here. So I'm choosing to put my non-inverting input terminal on top. I'm still going to draw VCC plus up here and VCC minus down here. Here's my inverting input voltage, my non-inverting input voltage. And so let's implement our positive feedback first. So this time I'm going to call this resistor R1. And then I'm going to put a resistor down here. That'll be R2. Okay. So there's my positive feedback network. Very similar to what we saw in our previous examples, except that effectively we're just grounding the leg of that resistor that's connected between the non-inverting input and a voltage source previously. Okay. Now, on the other side, we're actually going to employ a feedback resistor up here as well. So this guy employs, technically speaking, both positive and negative feedback, but because positive feedback is such a strong thing, the negative feedback's not really going to give any of its effects here. And then between the inverting input node and ground, I'm going to put some capacitance. And so this is our circuit. So what's the most glaringly obvious thing about this circuit? Well, okay, so there's a capacitor. That's definitely one thing. Where's the input voltage? There isn't one. There literally is not an input voltage to this circuit. Okay. So effectively, that means that this circuit is expected to generate some sort of output, even if we don't put any kind of input in. That's why it's called an astable circuit. Okay, it doesn't require any input whatsoever. It's just going to find stability at both a positive supply voltage and the negative supply voltage. And we're going to find out is it's going to change between those states at very regular intervals. Okay. So in order to figure out how this thing works, we are going to look at a couple of different things here. So I'm going to label this voltage as VC, which is just the voltage drop across my capacitor. And I'm going to label this voltage right here as effectively a reference voltage that the capacitor voltage is getting compared to. Okay. So because this circuit employs positive feedback, our reference voltage, or excuse me, our output voltage is always going to be VCC plus or VCC minus. And so our reference voltage is just a scaled down version of that output voltage because it's just the output of a simple voltage divider, effectively, right? This node right here is also VREF. And so we can see that it's going to be approximately equal to whatever V out is times R2 over R1 plus R2. Just simple voltage division there, nothing remotely fancy. Okay. So I'm going to make a couple of plots here. Let me scoot this over actually, so I can put 3 of them up here. So this guy right here is going to be VREF as a function of time. This guy right here is going to be VC as a function of time. And this guy right here is going to be V out as a function of time. Okay. So let's start by assuming that V out is equal to VCC plus and VC is equal to 0, meaning that our capacitor doesn't have any stored voltage or stored energy. Okay. So let's say that this voltage up here represents VCC plus, and this voltage right here represents VCC plus times R2 over R1 plus R2. So it's going to be the same polarity as the output voltage always, but the size of VREF is going to be slightly below the output voltage because we've got a voltage divider. So let's think about what's going on here, okay? So at this point in time, V out is equal to VCC plus and VC is equal to 0, which means some current is going to be flowing around this top path of the loop, right? That current is going to slowly cause the capacitor to charge over time. So our capacitor is going to slowly increase until it hits the level of the reference voltage. And then when VC and VREF are equal to each other, the output is actually going to switch to VCC minus. So effectively, this current over this top loop is just going to switch directions every half cycle. So V out is going to drop because our effectively our input voltage, as it were, VC, which is tied to the negative polarity, or excuse me, the inverting input terminal, once it exceeds the reference voltage, it's kind of working like an inverting comparator. It's going to push the output low, like so, which in turn makes this reference voltage low. And now the capacitor is at a higher potential than V out. So the capacitor is going to wind up discharging until it hits Vref again. And then that cycle is just going to repeat over and over and over. So it would look something like this. We'll see this in LT Spice in just a moment. So the period of our output signal is just going to be twice RC. Why do you think that RC is important? Because it's the time constant for an RC circuit. That's literally all this thing is. Times the natural log of 1 plus beta divided by 1 minus beta, where beta is just that voltage divider ratio of R2 over R1 plus R2. So effectively, those resistors R1 and R2 are kind of like fine-tuning resistors for this circuit. But the resistance R up top is the one that really establishes the time constant for oscillation and all of that kind of good stuff. And then the size of the capacitor value itself. So let's implement this circuit into LT Spice. I don't think I have a saved version of this, so I'll have to do it myself. I'm just going to make up numbers here, which means we're going to have to do a little bit of having to just find what an appropriate time for our simulation will be. But let's start by putting in our supply voltages. So let's just do plus and minus 10 volts. And let's throw our op amp over here. And now let's work on our feedback loops and all of that kind of good stuff. Oh, goodness gracious, what the heck happened there? I'm just doing all of this with wires, and then I'll add in my components in a moment. See, ground goes here and here. Resistor goes here and here. And also here. Capacitor goes here. And Let's make this guy 2K. I'm just arbitrarily choosing things. 3K, 10K, and 1 millifarad. Let's see, let me think about this. 2 times 10,000 times 1 times 10 to the minus 3. Looks like roughly 20 seconds per cycle. And then obviously times the natural log of that bit. Okay, so if I were to, let me label the output node here just for the sake of argument. Simulate this circuit as is. Let's do it for 100 seconds. And I click on my output node. My output voltage is 0, okay? Now, the reason why my output voltage is 0 is because we're dealing with ideal circuit components here. So I'm going to effectively give my capacitor a little bit of energy to start this cycle. And I'm going to do that by just saying that the initial voltage on my capacitor is, let's say, 0.01 volts. So just 10 millivolts, nothing, no huge amount of stored energy or anything like that. And because I labeled that node as VC, I'm going to label this guy as VC as well. And just for the sake of argument, let's call that other node VREF so that we match up exactly with what we saw earlier. So if I rerun this simulation, now I can see that very quickly everything starts kicking off. Just for the sake of argument, let's make this initial amount of voltage on the capacitor a millivolt. We can see it takes it some time to start swinging up, but it'll do it. So it really doesn't take much energy at all for this to happen, which is why we don't actually need an input signal. In a real electrical network, there's always thermal energy in our system because electrons move around. So that's literally enough to kickstart this thing. I'm going to do something here just so that we can kind of look at all three of these signals at the same time. So my output voltage was on bottom, which is exactly how I drew it earlier. So up top, I had my reference voltage, if I'm remembering correctly. So we can see that it follows the output voltage exactly, but it's just a scaled version of it. And then here in the middle, I have my capacitor voltage, and it's doing effectively exactly what I described, except that we're starting on a negative half cycle instead of a positive half cycle. So we were able to qualitatively describe what was going on, even if we didn't really bother too much with all of the math in the background that's making it happen. So like I said, this is a way for us to effectively make a clock circuit. We can make it change from high to low at regular intervals. So we can use this as a timing reference for circuits that need a timer without having to deal with like quartz crystal oscillators and all of that kind of good stuff. So just another application of positive feedback. Yes, Patrick.
I missed this part whenever you did it. How did you like give the capacitor like the starting?
So I defined it as an initial condition on the capacitor voltage. So this statement, sorry, I'm not trying to move it around.
How did you make it?
Sure. So let me get this thing out of the way. This .op command is how we enter in SPICE code. And we're going to be using particularly initial condition statements very, very soon when we're looking at transient analysis of problems. And I believe I used this statement when we looked at a simple transient analysis circuit on the first day of class as well. But it's just that .op button, and then you type in .ic for an initial condition. And I'm saying the voltage at the node VC, where the positive polarity terminal is at that node and the negative polarity terminal is at ground, which is just the voltage drop across the capacitor, is starting out at a value of effectively 10 millivolts. All right, so we are done for today. If anybody has any questions, I can hang around and answer them. If not, see you guys on Friday for finally negative feedback circuits. It'll be a little bit more gross until it gets infinitely better when we talk about ideal. Yes. Um, it's similar in as much as you have that dead band where it doesn't transition. So that's like, you didn't do a circuit like this, but the output is effectively the exact same thing. Yes. So something like this is so those the Schmidt triggers and all that kind of stuff are used for like HVAC control and all that kind of stuff to make sure that you don't short cycle the compressors and all that kind of jazz by having it constantly go off and on. So similar application even for temperature control. Yeah. But for the Arduino, you did it through code.